you know, he is a leading scientist of the present time who is working on fuzzy logic and fuzzy mathematics. Let me introduce Professor Castillo before his talk. He holds a doctorate in science degree in computer science from the Polish Academy of Sciences with the dissertation Soft Computing and Fractal Theory for Intelligent and Manufacturing. He is a professor of computer science in the graduate division, Tijuana Institute of Technology, Tijuana, Mexico. In addition, he is serving as research director of computer science and head of the research group on hybrid fuzzy intelligent systems. Currently, he is president of HAFSA, Hispanic American Fuzzy Systems Association, and first president of IFSA, International Fuzzy Systems Association. Professor Castillo is also chair of the Mexican chapter of the Computational Intelligence Society, IEEE. He also belongs to the technical committee on fuzzy systems of IEEE of NFIPS, IFSA, and IEEE. He belongs to the Mexican Research System SNI Level 3 and Emeritus. His research interests are in Type 2 and Type 3 fuzzy logic, fuzzy control, neurofuzzy, and genetic fuzzy hybrid approaches. He has published over 400 journal papers, 20 authored books, 100 edited books, 300 papers in conference proceedings, and more than 300 chapters in edited books. In total, more than 1,230 publications, according to Scopus, with age index of 99 and more than 33,500 citations, according to Google Scholar. He has been guest editor of several successful special issues in the past, like the Journals of Applied Soft Computing, Intelligent Systems, Information Sciences, Soft Computing, Fuzzy Sets and Systems, and many more. He has been elected Fellow of IFSA in 2015 and MICI Fellow in 2016. He has received the recognition as highly cited researcher in 2017 and 2018 by Clarivate Analytics and Web of Science. All in all, he is one of the torchbearers of the fuzzy logic community of the present time. So I would now like to request Professor Castillo to start his presentation.
Thank you for the nice introduction. Let me share the screen. Can you see the screen?
Yes, sir. It's visible.
Okay, so I will talk about Type 2 and Type 3 fuzzy systems, some theory and applications. Let me check if this is, can you see moving my slides?
In my system, the slide is disappeared, not visible. The slide is not visible.
Okay.
But initially it was visible. So
So
actually, share again. Share again. Sir. Now it is visible.
okay, so so I will talk about Type 2 and Type 3 fuzzy systems, some theory and applications. And this is a summary of my achievements. This is the group in Tijuana Institute of Technology. Question: my slides are changing or not?
Yes, sir. It's
Okay.
getting changed, but could you please make it full screen?
It's okay?
No,
No? Okay.
no, it got closed. So better please proceed with the earlier one. It's fine, visible. It's fine. It's fine.
Okay. So I will talk about type 2 and type 3. So just to remind you, the origins of this, of course, Professor Sade proposed the idea of fuzzy sets in 1965. Now we know that the original idea of Professor Sade is what we now call type 1. And so these type 1 fuzzy sets that he proposed that year are the initial proposal. And of course, that the theory of type 1 was developed in the years after 1965. Later, Professor Sade himself proposed type 2, although he did not work much more on that. I mean, type 2. Later, when Professor Mendel took over, the area of type 2 was developed more, and other people also started working on that type 2 fuzzy models. And I will talk about the differences later very quickly. So now, at this moment in time, we know that some problems can be solved sufficiently well with type 1, and others require interval type 2. Other ones, more complex ones, require general type 2. And of course, more recent research has shown that also type 3 can be used in some cases. Anyway, in any kind of system, we require to optimize parameters because the design of a fuzzy system for a particular application requires optimizing parameters or even the structure of the fuzzy system. So bioinspired or meta-heuristic optimization algorithms have been used very frequently to optimize fuzzy systems. And in this way, many applications have been cheap in control, robotics, parallel cognition, time series predictions, and other ones. But still, the question remains if even we have even more complicated problems, more nonlinearity, noisy, dynamic environments, and so on. Maybe higher types, orders, or extensions of the original type 1 models could be needed. And so here I will only talk about going in some way, we can say vertically, mean moving from levels type 1, type 2, type 3 in some way is in that sense, but also there are other extensions of fuzzy that I will not talk about here, like intentionistic, Pythagorean, Hessian, and other ones that are in the literature, but I will not talk about those kind of extensions, only in this direction of going from type 1 to type 2 to type 3 and so on. It's the one I will talk about because it's my research in this area. Anyway, just very quickly, type 1 was an extension of the original idea of a crisp or traditional set. So traditional sets only allow belonging or not belonging to a set, as you may know. So type 1 fuzzy sets proposed by Professor Sade allow membership to be any value between 0 and 1, although later it was shown that this was not really a representation of uncertainty. Theoretically, Clear and Yuan show that this only describes vagueness in this case for the sets. So uncertainty was really handled by type 2, and that was realized. And of course, even with this type 1 is sufficient for many simple problems. So it's important also to know that. Anyway, why do we need type 2? And so here is just a simple example. If we want to manage the concept of toll, when people are called like this, being told means that subjectively for us, for any of us, Maybe a person is tall with a certain height in meters, but if we use a fuzzy type 1 fuzzy set, we use a membership function like the one shown here, which is a triangular. So a particular height will, in meters, will give us a membership, but the membership will be a numeric precise value. So this is type 1. And of course, this is an, an, an advancement to the idea of a set in some regard, but it's an improvement in some way, but this is not the complete representation of uncertainty, because actually this numeric value of uncertainty, sorry, of the membership to being told is not representing the whole uncertainty of the concept or the idea of told in this case. So if we want to be better at representing the uncertainty in this case, we could use something like, well, the membership is about 0.62. Instead of just giving this precise value of 0.62, we will say about 0.62. And about 0.62, if we use an interval around 0.62, this will be interval type 2. And if we use another type 1 fuzzy set to represent the uncertainty of about, this word, this linguistic way of saying around 0.62, then we will have a general type 2 fuzzy set. So actually, many people don't distinguish about this interval and general type 2. Many people, many researchers just, they say type 2. In some cases, they are referring to interval type 2. In some cases, they don't know that actually there is general type 2 and interval type 2, so you have to be careful with this. But there are two types, or two different kinds of type 2, interval and general type 2. And the difference is in the way that we represent the uncertainty over the membership, the initial membership. In the interval type 2, we use an interval around the membership, and in the case of general type 2, we use actually another type 1 fuzzy set for the uncertainty of the primary membership that we have, like in this case is the 0.62. Anyway, so in this way, an interval type 2 fuzzy set is defined as shown in this equation or this expression. We have an element x, the primary membership that is used in the type 1 fuzzy set definition, but we have a secondary membership, but in the case of interval type 2, the secondary membership is assumed to be fixed to 1. So the secondary membership is uniformly valued to 1, and in this form, it's like an in-between case. It's not the full type 2, not the complete type 2 fuzzy set, because we are assuming the secondary membership to be uniform or fixed. The advantage of using interval type 2, of course, at the beginning was very important, is that we only need to characterize interval type 2 with using two membership functions, the upper and the lower. The upper and lower membership functions are type 1, and they are limiting the interval type 2 fuzzy set or the interval type 2 membership function. And so we have something like this. So instead of just having the simple triangular membership function, in the case of interval type 2, we will have an area which is called the footprint of uncertainty, or FOU, the area inside the upper membership and the lower membership. So we have two limiting type 1 membership functions, the upper one and the lower one. And inside those, we have the footprint of uncertainty, which is an area, in this case, which in theory tries to model or represent the uncertainty of, in this case, of this concept, the concept of toll. The meaning of toll, in this case, is the uncertainty is in semantical, or in the semantics of the meaning of toll. Actually, inside this area, we have an infinite number of type 1s. An infinite number of type 1s are contained inside, which in theory represent the different meanings for different people of this concept. So in theory, we will like to have that all meanings are supposed to be for the meanings for different people, because it's a subjective concept. are contained or should be contained inside in this case. So this is the idea of interval type 2. And so for a particular height, instead of just having a precise value for the membership to this concept or the membership to this set, we have now an interval with the lowest value and the maximum value, and inside the interval are contain all the different other values that could be for the meaning that different people could give to this concept. So that's the idea of interval type 2. And of course, by doing this, we have to extend some things I mean, in the when we use these type 2 fuzzy sets, the fuzzy system that we will have will require more computation, of course, because we are extending or generalizing in some way. And the first thing that we have is that at the output, if we have that the output of a fuzzy system is an interval type 2 fuzzy set, now we will require two steps or two stages to calculate the final numeric value. Before in type 1, we only needed declassification, but now we will need two operations, type reduction and then declassification, because type reduction will be a similar operation to declassification, but will reduce from type 2 to type 1. And then after that, we will need to calculate from the type 1 the representative number, which is the classification process like a centroid. In general, the two steps are like centroids, but the centroid done in type reduction is done over the 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 membership functions that are inside the footprint of uncertainty are used, and then after that we will have a simple, more simple fuzzy set that will only be reduced, I mean, by the classification. Just this is done here. I'm just explaining very quickly the idea, not going into more detail in this moment because of time. Anyway, the problem here was at the beginning, around 2000, at the year 2000, was that how to find out the two particular type 1 fuzzy sets or membership functions that will be needed to be able to reduce the interval type 2 with those type 1s, so that the approximation of the result will be good enough. And theoretically, Mendel and Liu find out that there are two particular points called switch points that, in this case, I'm illustrating here in this figure. These are the switch points, CL and CR, left and right. These two switch points actually are called switch points because it's a point where we switch from the upper membership function to the lower one. You can see in the red one, this is a particular type 1 membership function, or type 1 membership function is the best way to say it, that is part of the upper and part of the lower. And actually the other switch point, the right one, will be part of the lower, and then you switch to the upper. And these two type 1s are the ones that we need to just at the end perform the average of both of them to find the final result. And the problem of finding the CL and CR is an optimization problem. And actually, Carnegie and Mendel did find out an iterative algorithm that by a sequence of steps approximates the left and right switch points, and after that you can just do the average over them, over the two type 1 membership functions that I was talking about. Actually, in practice, 3 to 4 steps are sufficient to get a good enough approximation, and for many applications like in control, for us, we are very happy with that because we don't need to have an exact, very precise value, but just sufficiently good result to control, for example, a robot or something like that. Anyway, even with that, even at the beginning and in the decade from 2000 to 2010, This was very good because we were able to implement interval type 2s in control or other applications. And also we did use hardware implementation like with FPGAs to do this faster, even faster in hardware. And that was very important at those times. And in summary, this is the architecture of this kind of interval type 2 system for the Mamdani kind of fuzzy system. Anyway, so we have falsifier, we have rules, we have inference, similar to type 1, but at the output we have type reduction to reduce type 2 to type 1, and then the classification to reduce from type 1 to type 0, which is a number. And in some cases, the output could be if we need something fuzzy like or an interval like in prediction, maybe the output could be here, or in computing with words like in processing natural language processing, we can input words and output words in this same scheme. So but in control, for example, or other applications, we need a number, so we need to go to the final part of getting a crisp of numeric output. And so in that case, we need to do these two steps. And at the beginning, this was the bottleneck in computing fast enough these results. And so for certain applications, it was a problem. For other ones, not. But this is the idea. So anyway, we can go one step more in the generalization. And so one step more in the generalization is going to general type 2. And this is very important because, as I was telling you before, I see many papers and I review many papers, and you can imagine, and many researchers just say in the paper type 2. And we have to read the paper to realize, I mean, as a reviewer, that they are actually doing interval type 2, for example. And in rare cases, very few cases, they are doing actually really general type 2, which will be the complete type 2. Given my meaning, my idea, my own say. And actually, in general type 2, the secondary membership is another membership function, not fixed to 1. As you remember previously, on the interval type 2, the secondary membership was fixed to 1. So everything is on the plane, like I was showing in this video. So, but now in general type 2, the secondary membership function is actually another membership function, another fuzzy set. So we have a fuzzy set, type 1 up to this point, and another fuzzy set over that one. For each point in the primary, another fuzzy set to represent the uncertainty of the primary values. And so in this case, this is the representation. Now we are on 3D, three-dimensional, because now we need the third dimension. We need to represent that the uncertainty on the secondary membership is not fixed to 1. It's actually, like in this case, a triangular, so it's the membership is lower on the extremes and higher on the middle of this interval. Before interval type 2, we only use the interval because we assume that the secondary membership was fixed to 1 or uniformly valid to 1. But now we have that the secondary membership function is actually not uniform. Is in this case, for example, triangular, and it's going up out of the plane. So we need the three dimension or the three-dimensional representation in this case. And of course, this is more computationally demanding. It requires more computation, as I will very quickly show later. Actually, what we do, there are several approaches, but one of the approaches is to slice horizontally this membership function, and each cut horizontal slice in this case is a plane in 3D, and it's like an interval type 2. So each slice is an interval type 2. And so we slices a number of points, a number of samples. For example, 10 slices will be 10 interval type 2s to approximate a general type 2, or maybe 100. So you can imagine the number of calculations that we need to do in this case for general type 2. And so this delay, of course, the advancement of general type 2, maybe, if I can recall, around 2017, 2018, finally we were, I mean, in my group in Tijuana, we were able to compute fast enough general type 2 to use it in control or in other applications. So before that, it was too slow. We only could do it in simulations, and we waited for the result. But to do it real time, I mean, we needed to process very quickly, and we were able finally with better algorithms and better computers to do it more quickly. Anyway, mathematically speaking, I will not show more detail, many details about this, but we have generalizations of all the operations, as you can imagine, for like intersection, union, and so on. We have more general operations, and of course, mathematically, there are people working on generalizing all mathematics with this kind of fuzzy sets, and so we have generalizations of fuzzy differential equations and fuzzy algebra, fuzzy algebraic equations with general type 2 or interval type 2. There are people working on that, of course. And I will not speak about that, but it's very interesting. These are the way that general type 2 is represented here with shaded colors, because we don't want to show 3D, but actually there are three-dimensional language functions. So here we have this kind of inference. In this case, for singleton inputs, I mean, singleton will mean give the system numeric precise values. But if we were to have non-singleton inputs, which will be fuzzy sets as inputs, we will have this kind of inference. And actually, another thing here very important is that most people, they do not, again, they do not say explicitly. Actually, most people use or they are doing singleton fuzzy systems because they use numeric values as input and take a numeric value at the output. But some few of them are using non-singleton fuzzy, which is more interesting and more realistic, because actually information or data coming from the environment is not precise. It has also an uncertainty. If we want to have this represent this as uncertainty, we will need non-singleton. But most people do singleton because it's more easy to compute and more easy to understand. Anyway, around the year 2008, 2007, 2008, we were really pressured by, I mean, all the researchers in the world to show, actually in fuzzy, I mean, to show that actually type 2 could be better than type 1, because we were working on something more complicated to compute and more complicated theoretically. I mean, so if we were not able to show better results than type 1, it was not needed actually for practice. So several of the researchers working on type 2 at that time, including us, we needed to show some proof numerically and experimentally, simulations and experimentation. And one of the first papers where we were able to do that is summarized here very quickly. We used a control application with very simple design, just the error and the change of the error, granulated with three membership functions: negative, positive, negative, zero, positive, error, change of error the same, and the output will be control action U. On the left, the type 1 design; on the right, the type 2 interval type 2 design. The same same kind of membership function, Gaussians, but with footprint on the right, which means they are interval type 2. And we use this classic feedback control, where we have here the fuzzy controller, type 1 or type 2, here a plant or a system like a robot. The output is the actual, for example, velocity of a system. We measure this variable and we feedback here to compare it to the desired or reference value, and this gives us the error and the change of the error. But actually in practice, this is not perfect. So we have noise and perturbations. For example, if we consider that there is noise when sending the signal from this point to the beginning to the input, uh, Gaussian noise was assumed in simulations in this part for this mathematical model of a plant, and we can measure with the usual metrics in control, some of the square of errors, some of the absolute value of errors, or the time multiplied by the absolute value of errors. These are three different kind of metrics that are used in control for designing different kind of controllers. And we wanted to see the errors. And we compared when we had type 1 or in type 2 under no noise. So this will be like an ideal situation or system. And then when there was noise in the feedback, like kind of a real simulation in some way, and when there is no noise or uncertainty in the feedback of the controller, the signals here, type 1 is blue, type 2 is red, we can see that almost the same. Actually, even in some cases, type 2 is slightly higher because it's not needed when there is no noise. But if we consider noise, here I'm showing the, the three metrics, absolute, sorry, the sum of square of errors of time, absolute value of errors and time multiplied by the absolute value of errors is the one below. And you can see very clearly that type 1, which is the blue signal, is higher in almost all instance of time. Here is simulation of 200 seconds. So the sum of the errors is, of course, very high for type 1, which is the blue one, against type 2, and we can see it in the table. And if we change the level of noise, we can see that higher levels of noise give us a even higher difference between type 2 and type 1 in favor of type 2. And if the noise is decreased, then type 2 and type 1 will tend to be the same behavior, almost same error. And so this was one of the first papers where it was really shown in control that type 2 could be better if there is noise or changing environment or perturbations. It could be that the results of the type 2 control, even if it was a little slower, could be better, the error at the end, which means that for example, a robot is following a trajectory very close to the desired trajectory that we want to have, or even if we have obstacles, can avoid them very efficiently. So later, after that, we were able, and also other researchers, to see it in real physical robots. Of course, with real robots, the errors are higher because there are more variables that we are not considering in a simulation. A simulation is with a mathematical model, in some cases, very simple mathematical models of that real system. So with a real system, the errors and the difference are even higher than shown here. Anyway, so here you can see the kind of following the trajectory. On the right is type 2, which is closer, so that's why the errors are lower than in type 1. So more quickly, going into more recent developments, just I will say some things. For example, there are works on not doing iteratively, finding the switch points just directly with formulas derived so actually we derive equations to calculate directly in one step, if you want to say like that, the approximation to the switch points with some methods. We have applied this kind of interval type of system for parameter adaptation in meta-heuristics. We have shown that actually using, for example, type 2 fuzzy controllers is more robust, or we have more robustness to noise, because having a type 2 fuzzy system is like having an infinite number of type 1s. So actually, each type 1 embedded or inside the type 2 will respond differently. So it's like having many type 1s being able to respond to different situations. So that's why it's more robust. So if you have higher and higher levels of noise, type 2 will still be doing a good job and type 1 will get lost. So for example, if you're controlling the robot will get the loss instead of going up or following a trajectory if you have a very high perturbation to the system. And Another way that we have reduced the complexity of general type 2 is using a concept proposed by Professor Perez, which is called shadow sets. If we use a shadow set, we can only use two interval type 2s to approximate a general type 2. So in this way we are doing something similar than before when two type 1s approximate the interval type 2, we were able to use two interval type 2s to approximate a general type 2 with that concept. And we also have work on the aggregation, which is done at the output. It's kind of an integration of many type 1 fuzzy systems. And we can use numerical methods like integration, the Newton codes or things like that to aggregate in a better way the outputs. So there are many things that you can do in the theoretical side, and you can improve results. You can also do sampling when this is for when we have a lot of data. You can design many type ones, and you can then build the footprint of uncertainty based on sampling many type ones. They want fuzzy sets to construct or to build the footprint of general type 2. In this case, was done for medical application and medical classification problems. And you can optimize the design of the footprints of the form of the image functions with this using, for example, meta heuristic or the inspired optimization methods. Now let me go to another step more, which is type 3. So now we use, if we go in the same way that I was telling you before, that in type 2 we use a secondary membership. Now in interval type 3 we use a tertiary membership function. So actually you can see here that we have the primary, which is using type 1, then a secondary, which is using type 2, and then a tertiary, which is using type 3. So the tertiary will give us the uncertainty over the secondary, and the secondary will give us the uncertainty over the primary. And now we are at the stage that we are using the tertiary fixed to 1, like it was done before in type 2. So when we use this tertiary membership function fixed to 1, we actually are doing now, because of complexity, interval type 3. So most of the papers you can see now on type 3 are interval type 3. We got accepted one paper this past month on general type 3, where we are proposing some things to do general type 3 in a faster way, but it's still on process. So anyway, interval type 3 is assuming the tertiary being fixed to 1, and now we have this kind of membership function. For example, these are scale Gaussians over scale Gaussians. If we slice it, in this case, horizontally, we have this kind of membership functions, and the footprint is built with the union of these slices. The footprint here is this part in green is part of the footprint that we have in this case. Anyway, in this way, I'm showing the operations. I mean, union on the top right, intersection on the below left, and negation of the union. So here is just with figures. Of course, we have mathematical expressions for this, which are generalizations of the general type 2 operations. And the idea here is that secondary membership in interval type 3 are interval type 2 versus in general type 2 secondary membership is type 1. So they are built on top of the other ones. And so, or another way to say is the upper and lower levels of the footprint in type 3, interval type 3, sorry, are interval type 2. So that's the way that this is done. And of course, for general type 3, will be general type 2, the upper and lower levels. And so you can get my idea with that. This is one another representation that we can make of this. This is from one of my colleagues, Ardashir, from Iran. This is kind of figure that he uses to explain it. But this is the same thing. And actually, we have shown that it works in practice. This is a controller of a temperature controller, where this was published in the National Journal of Physics System in 2001, sorry, 2021. Uh, and Actually, we compare it against general type 2, interval type 2, and type 1, and produce better results, lower errors, I mean, interval type 3 controller. And also there we have other papers in control, like this is for balancing voltage in microgrids. And we have used it also not only in control, also for prediction. I mean, predicting with passive systems in this case. Also for quality control evaluation. I mean, in this case, previously we have done this with type 2, and we wanted to test with interval type 2 to see if we could get better results. And we have also done this for adapting parameters for example, in this case, for differential evolution, which is a meta-heuristic. And this was applied to design the interval type 3 fuzzy controller of a robot in this paper. And also for B colony, we have done the same thing. And we have now done this for real robots in our lab. And I will skip some things because of time. So this is the kind of controller using the sensors as inputs, and they can control this robot to avoid obstacles and to follow trajectories. And actually, this is this robot has a simulation environment, and then we test with the real system, and we can see that going to type 2 actually here reduces the time it takes the robot to go around a cycle, and because it can go faster, and the errors around the side trajectory are lower. And now my student is doing also for general type 2 and type 3. And with colleagues from Turkey, we have also controlled the real mini helicopter system. We have tail rotor and air rotor, and we have two controllers, one for each rotor. In this case, we have the rule base from the experts for controlling the rotors. And this is the system in the lab, is from the lab in Turkey with my colleagues. And we can see the errors compare against PID. And we can see that the errors are lower with our system than with the classical method. And also we have shown that it's better than type 2, type 1, and intuitionistic, because actually my colleagues, they were mostly, they have worked in intuitionistic fuzzy control, and they wanted to explore other methods. So we collaborated to test our methods. And also this has been done for adapting parameters in meta-heuristic, like I told you before, like in this case for B colony. This is a kind of general type 2 membership function I told you before. And if we slice it horizontally, we have this kind of interval type 2. It's similar to using alpha cuts, but here we have alpha planes. They are called alpha planes. So the controller for the robot is very simple. You control two wheels, the left and right, two outputs, and the inputs are the error and velocity, angular and linear velocity, two inputs. This is the kind of robot, two wheels to control. And the rules are very simple to find the rules to move the wheels. Positive is forward, negative is backward, zero is no movement in left or right wheel. And also we have rules to control the parameters, in this case, of the B colony. The B colony optimization algorithm has equations to move from one point to another with probabilities. And alpha and beta are the parameters that, depending on the values of alpha and beta, the B colony can converge faster or slower. And we have rules to control alpha and beta. So it's like having a controller over the VCO, fuzzy controller, so that the fuzzy VCO can improve the result of the fuzzy controller of the robot that we want to have. So this was done by one of my PhD students about 5 years ago. The inputs for the control of the parameters are the iteration in which we are at the moment. So iterations are low, medium, or high, depending if we are at the beginning, at the middle, or at the end of the iterations of the bee colony. And diversity is the difference between the individuals. As you know, this algorithm use a population of individuals, in this case of bees, so that they are trying to find the solution. That's the metaphor that they use in this case. So here is the type 1 fuzzy system to control the alpha and beta parameters. Then we extended to interval type 2, and we extended to general type 2. And now, as you see before, now my colleague, she was my student, now she did it the same thing for type 3 in this case. So these are the rules to control alpha and beta. She did find the rules by experimenting with the algorithm, and so in that she was able to see when beta or alpha will need to be low or high or medium, so that the result the convergence will be faster for the system. And actually, not only that, but also the result of the final controller was better. Here I'm showing trajectories. The robot need to follow the red signal, but actually the robot is wiggling because of perturbations around the trajectory, because it has to evade obstacles or something. And so the error using just a simple VCO is this kind of value. Using control of the VCO with type 1, interval type 2, and general type 2, and you can see the error reduces, and the trajectory is, the robot is, the trajectory is the one in blue, is getting closer to the actual trajectory that we want to have. And for type 3 was, of course, even better. So let me conclude by saying this is a very quick view of my work for many years. So I have been working since 1998, when I met Professor Sade in Anchorage, Alaska, and I was motivated to work in this area. Then I started working in type 2 since the year 2000, when I knew Professor Mendel and later other professors. And so I'm always motivated by applications, not only theory, but I do some theory also. And some of my books and publications you can find in the internet, or in Google Scholar or ResearchGate or others. You can see the books, and actually this is the book where you can find more details of type 3, and this is from 2022. And now we are preparing more things. Maybe a new book will be done more, maybe next year, with more new things in type 3. So thank you very much for listening to my work, and I don't know, because I don't know how much time I took, so I don't know if there will be time for questions, but thank you for listening.
Thank you very much, Professor Castillo, for such a wonderful presentation, showing the theoretical background behind the application in real life, especially in robotics. Now I'd like to request the audience if they have any queries or questions to Professor Castillo. You may ask.
Hello, sir. Actually, I have used fuzzy logic in MATLAB, Mamdani Sugano type, but I'm interested now in type 2. So, is there any software or MATLAB is enough, or will you suggest any software for
MATLAB
implementation?
Since I think 2020 or 2021, there is an interval type 2 toolbox in MATLAB. And actually, it's very interesting because they have a function there. So if you have a type 1, you can directly convert it to type 2, interval type 2. So that makes it very easy for anybody to, if you have already a type 1, with that function, you can convert it to interval type 2. And then you, of course, you will have to maybe change parameters, to optimize it. But anyway, it simplifies. They don't have general type 2. I
Okay.
think maybe because of computation,
Let's
but
see. Yes.
there are few there are some academic software on general type 2. For example, there is one in Java by a group in England. We have also some software on general type 2. And but if you at least want to begin with interval type 2 in MATLAB, there is also in Python, there is a new, there before there was only type 1, but a researcher from Iran, he proposed an interval type 2 toolbox also in Python. So
Okay.
we have
Okay.
used both because some robots are very easily controlled in Python using a Raspberry Pi chip or hardware. And so you can, in some cases, maybe better with Python depending on the problem or your system.
Okay, sir. Thank you.
Okay.
Sir, I just want to have one query that many people are working on fuzzy aggregation operators and mainly on type 1. So, do you think that those operators can be applied to type 2 and type 3 also?
Yeah, I mean, they can be extended to type 2 and type 3 and even type N. There was a paper last year on type N by John Ricard. He works in the US, which is mostly theoretical, but in theory, you can put the theory for type N. And, uh, and of course, type 3, type 2, and type 1 are special cases of that theory, no? But yes, I think they can extend it. The idea will be to model uncertainty better. And, uh, and of course, we have to always remember that some problems may be sufficient type with type 1 to solve them. For example, controlling a washing machine or the classical cases, controlling something like that, domestic appliances. Maybe with type 1 is sufficient because you only need 3 rules or something like that. But more complex problems in noisy environments, like a robot moving around or a drone in flying. There's a lot of noise to be considered, but also in decision making, many many uncertainty sources can be present. So maybe type 2 even more could be used.
Thank you, sir. Thank you for enriching us. And before conclusion, I have one announcement. It's a pleasure. Let me show the screen. Everyone can.
Dr. Nayan.
Yes, sir.
So ask the participant, is there any question from the participants?
Yes, sir. From the audience, there was a question. Professor has clarified it. And also, if there are any other questions, we are ready to take it. Is there any more questions? No, I think there are no more questions. So, before conclusion of this session, I present one certificate. I would like to show you one.
Rukumar, kindly show the certificate on the screen.
It's with me also. I can show.
Okay, if show the certificate, I am declaring. So Professor Castillo, so thank you very much for your nice presentation and your highly effective or highly contributed works in fuzzy mathematics, particularly type fuzzy sets. So the Sridharacharya Society, Academy of Mathematical Society is very pleased and honored to present a Lifetime Achievement Award to Professor Oscar Castillo of Tijuana Institute of Technology for his groundbreaking contributions to fuzzy logic and its application, especially his work on type 2 fuzzy logic and fuzzy control theory. His research has led to significant advancement in the theoretical foundation of fuzzy mathematics and has provided demonstrable benefit in solving complex real world problems. So we are very pleased to or and honored to uh, confirm this lifetime achievement award for his those amount or groundbreaking research work on fuzzy math. So kindly accept your award.
Thank you very much for confirming the work. Maybe you can
And
send me
big round of
by
applause
email.
to Professor Castillo, everyone.
Thank you.
Show the certificate and we will send it by mail.
Is it not visible?
Not visible.
Isn't it visible? I
Share
have
the,
shared it.
share the screen. Share the screen.
I have already shared it. It's not visible.
No.
Okay, let
Till
me
now
share
not
once
visible.
again. Let me share it again. Is it now?
Yes,
Ah,
yes.
yes, I can see it. Let me take a photo. Thank you. Thank you very much. Maybe you can send me by email later.
So, thank you very much, Professor
Thank you.
Castillo. So the next session is an invited talk